This session we are going to discuss about the few examples for the characteristic function. The characteristic function, the probability mass function is given. You have to find out the characteristic function. The random variable x can take on the value x1 equal to -1 and x2 equal to 1 with probability, equal probability. You have to find the characteristic function. This is one of the property of the characteristic function. Probability mass function is given. You have to find out the characteristic function. Another property of the characteristic function is characteristic function is given. Use the inverse theorem of the characteristic function. You can find out the probability mass function. This is the uses of the characteristic function. But another example for the characteristic function is you have to find out the characteristic function for the given function, from which you have to first order differentiate it, then give the zero value. You will get the raw order moments m1 0 and m2 0. Then you have to find out the mean and variance. In this first example, the probability mass function is given. You have to find out the characteristic function. Then as usual, the definition of the characteristic function, expectation of e to the power of itx, that the x probability take two values x1, x2, the probability mass function value is -1 and +1, that associated probability is equal probability 0.5. So this is jump point, first p1 and p2, that p1 you have to 0.5, then the e to the power of itx and the p2 0.5 e to the power of it. Therefore 0.5 is common, then e to the power of it plus e to the power of it. This is called, this is the cos t function, e to the power of exponential series is the cos t. Then 2 into 0.5 cos t equal to, therefore cos t is e to the power of it plus e to the power of -it by, this is the trigonometric function, cos of t. Therefore for the given probability mass function, the characteristic function is phi t equal to cos t. Then we are going for that. The density function is given. You have to find out the characteristic function. So in that earlier the probability mass function given, but here this is the probability discrete case. This is the continuous case. That x is less than 0, then x lies between 0 to 1, then x is greater than 1. There is three values. This is called the uniform or rectangular distribution, for which you have to find out the characteristic function. How you have to find out the characteristic function? There is three integrals. The first integral limit you have to apply, second integral you have to limit apply, third integral you have to limit apply. Therefore phi of t equal to expectation of e to the power of itx minus infinity plus infinity f of x into e to the power of it. So for the given continuous case, there is three limits. You have to first integral, second integral and the third integral, for which you have to apply that minus infinity 0, 0 to 1 and 1 to infinity. You have to subdivide this entire integral into three identical integrals, substituting the upper limit and the lower limit. That is minus infinity to 0, that is 0 e to the power of itx dx. This is the f of x second integral and the third integral. Therefore integral of 0 to 1 e to the power of itx and dx equal to upper limit and lower limit you are substituting, you are getting 1 by it e to the power of it minus 1. So this is the, for the given continuous probability density function, this is the characteristic function. This is another example. And as usual for the any theoretical distribution also you can find out the characteristic function. After obtaining the one of the property of the characteristic function, you have to differentiate and substitute the value, then you can find out the mean and the variance. That given value is there, x equal to random variable have a Poisson distribution. Then you p of x equal to k, let's say e to the power of minus lambda, lambda to the power of k by k factorial. K takes value finite 0, 1, 2. For the probability for characteristic function, expectation of e to the power of itx equal to summation of k. Therefore you have to substitute the value for 0, 1, 2. You have to substitute the values for 0, 1, 2. This is the e to the power of minus lambda. This is 1 plus e to the power of x by 1 factorial plus e to x to the power of 2 by 2 factorial. This is the exponential series, that is e to the power of lambda e to the power of it. So this is the characteristic function of the given Poisson distribution. One of the application of the characteristic function is you have to first order differentiate. You will get the e to the power of lambda e to the power of it minus 1 into lambda e to the power of it. For the first order differentiation, you have to substitute in the value equal to 0. Then you are getting the raw moment m1 equal to lambda, because you know that m1 equal, we already proved m1 equal to first order differentiation substitute 0 by I dash. Then you have to find out the raw moment of the second order. From the first differentiation, you have to find out the second order differentiation using the chain rule. I e to the power of lambda e to the power of it minus 1, lambda e to the power of it lambda e to the power of it into I plus. You put as constant, then you have to differentiate the other form of the UV form. Then you have to substitute in that I equal to 0. You are getting the term I squared u to the power of 0, u to the power of 0, and this term is reduced to lambda squared plus lambda u to the power of I squared. Then you have to, after substituting for the second order raw moment, second order differentiation, substituting 0 by I squared, you are getting the value of lambda squared plus lambda. This is the relationship between the raw moments and the center moments. Therefore, variance mean equal to lambda. We prove that mean equal to lambda. Variance equal to m2. That is the second order differentiation value minus first order differentiation square. Second order differentiation value is lambda squared plus lambda minus lambda squared plus lambda. So this is the variance. So today we discuss about the uses of the characteristic function for discrete case and the continuous case, and using the inversion theorem application we discuss. Is there any doubt you can ask?